Yeah.
Because unless you could,
Had a long time ago.
it'll be like,
Yeah, the stand. Yeah.
you're just like, I know this, but if I cross both, or you're like, you always can't narrow it down. No matter what it is.
Yeah, I just saw like
Well, no, I haven't dropped I might end
Like I want to go into it. I don't want to be out there.
All right. Let's go ahead and get started on new material for today. So we're going to start following the book pretty heavily. We did our math review, okay? And so after this math review, we're starting in on chapter 1.
Are we done?
Yep. You're all ready now.
We are.
To begin.
And if you're not ready, there's plenty of other problems out there. We can, if you're struggling to find some problems to do, I can come by and I'll get you some, okay? So the homework for this week is just in the book. Please don't look it up online, how to do all of them. But it'll be problems 1.1 through 1.11. Okay? And that's it, 11 problems this week.
What page is that?
That's page 13. The 1 means chapter 1. Okay. And that's, well, I mean, I like the problems in this book, that's why we got Alright, so this first problem, this first chapter is called kinematics. Kinematics.
That homework is due Monday?
Yes, this will be due next Monday. Actually, I think next Monday is Labor Day.
Yeah.
Tuesday?
So I believe it's next Tuesday. All right, so chapter 1 is called kinematics. What kinematics means is position of an object given an acceleration and possibly an initial velocity. So basically, it's the relation between acceleration, position, and velocity. And we'll have to talk about what each of those things mean. Relation between position, acceleration, and velocity. All right, so first of all, we've already mentioned this a couple times last week, position. If I want to describe where an object is, I'm going to be interested in the position of the object. That's what it means. Where is an object? And so the position vector is defined with respect to a coordinate system. So let's say I have an XY coordinate system that I've defined. Just written down. Imagine placing this on a map, just drawing it on a map. I'll call this point the origin, sometimes labeled with an O. And if an object is over here on the map, after the position vector would be an arrow pointing from the origin to the position of the object. So position vector usually labeled with an R equals arrow pointing from origin of coordinate system to position of the object. Pointing from origin of coordinate system to object in question. And then this is the position vector. Okay. All right, so that's just how we define the position vector. An example of this would be, let's say I have a map and I have north, east, south, and west, and I put my origin at Hays, Kansas, and let's say that Topeka or something like this was about 200 miles this way, and where this angle here, as a crow flies, maybe about 5 degrees. Okay? Then this would be the position vector of Topeka with respect to Hays. Okay? Or if I can imagine, I defined in terms of an object. Imagine I'm interested in a car in Topeka. This would be position of the car. That car with respect to Hays. Okay? Makes sense how we define the position vectors. All right. And then you could write this out in components by calling this the x direction and calling this the y direction. And then you could say that, for instance, R would be 200 miles cosine 5 degrees x hat plus, or actually it's in the minus y direction, 200 miles sine of 5 degrees y hat. See, and then that would be the vector. Make sense? Okay.
Oh, yeah, sorry.
All right. Good. And you can add these two vectors together. You could add multiple position vectors together. There's not two of them here, but if you wanted to, and then get the position of the final vector. These things are just like normal vectors. These are just vectors.
So is R the hypotenuse for that?
The total distance is at 200 miles. The 200 miles is the magnitude of R. Okay. Make sense? All right. Let's go ahead and see what happens. Let's say I have an object that's moving. A moving object. So imagine you have a car, and initially it starts out at this point, and then it moves out for some other time to over here. So it's moving this way. I'm going to call this the initial position. Initial means the beginning, and the final position. And we can label those, it's as R with a little I here for initial, and R with a little F here for final. Okay, so this would be the initial position vector, a final position vector. These would not be the same if the object's moving. Let's say that the object moves from the position Ri, initial position, to final position in a time t. We can introduce something called the change in position or displacement. So if I'm interested in the change from position from Ri to R final, I could draw the following vector. I'm going to call it delta R. And in this case, Ri plus delta R. Let me draw this white. Ri plus delta R. This is the change in position. It's going to be equal to the final position. Can you see how? And you can see this because the way we added vectors is we add the tail of one on the head of the next. And so this Ri plus delta R added together is R final. Make sense? Or this displacement vector delta R, or change in R, could be written as the final position minus the initial position, where I just bring this vector over to this side. Okay, this is called displacement. Or how much an object moves. All right, the velocity vector, and we know velocity is a vector because it has a size and a direction, would be to describe how things move. We'll label it with a V, and that would just be, the definition of it is that displacement vector divided by the time it took to move from the initial to the final position. And this would be the average velocity in that time t. Let's go ahead and do some examples of this. So let's suppose that a person is walking, and they walk so that they, well, okay, let's see. Let's do something simpler to start out with. Let's say a person is walking in the east direction, which we'll also call our x direction, and they start out at a position of 1 meter from some origin, and at a time 5 seconds later, they're at 8 meters. It's not drawn to scale clearly. Okay. What is their velocity? What is V? Question mark. And so I'll do this problem, I'm going to give you one to do on your own. So this one, what we can do is we'll just look at the initial vector. What's the initial vector? Our initial would be 1 meter in the x direction. Final vector, that was 8 meters in the x direction. So Ri, delta R is going to be equal to R final minus R initial. which is 8 meters x hat minus 1 meter x hat. If I subtract the vector, that's the same thing as just subtracting the components. So this would be 7 meters x hat, right? And so velocity is going to be delta r over t, or change displacement divided by the time. That'd be 7 meters x hat divided by, what was it? 5 seconds. So that'd be 7/5 meters per second x hat, or 1.4. And that's your velocity vector. You got that from looking at the change in two positions. Let's do something a little bit more complicated, and I'll let you guys give this one a try first. Again, I'm going to introduce a coordinate system. I'm going to say x and y. And I'm going to have a person walking again. But this time, they're going to walk, and they're also going to walk straight east, just like before. But this time, they start out at 5 meters above the origin, and this is 3 meters and east of the origin, and then this final position will be 10 meters east of the origin. Actually, let's make it consistent with this one. We'll just do the same type of difference. Let's say that that's 9 meters east of the origin. And let's say, once again, it took 5 meters to go from the initial position to the final position.
5 seconds.
So yeah, 5 seconds. Thank you.
And it's to like 5 minutes long.
Yep. And then this is straight east still. From our initial to our final. And you can guess that you should end up with the same thing as this. Go ahead and check it, right? But write out those vectors carefully. Raise your hand when you get done with going through this one. I'd like to see you write up the vectors. Yeah, very simple. So let's illustrate something. The points where the real estate things so we have this coordinate system. Alright. So that one too simple? Alright. That point of this one, by the way, is to point out the fact that look at that origin of coordinate system for position won't affect the velocity vector. Okay, so it doesn't matter what your origin of the coordinate system will be if you're interested in velocities. Because all you're doing is you're looking at different positions, and that doesn't depend on the coordinate system.
You're looking at the movement, not where it is.
Yeah, exactly. Do we do another one, a little bit more complicated?
Well, can we do those?
Yeah.
Okay, we'll do this one, just to get the vectors. So our initial is going to be 2 meters x hat plus 5 meters y hat, right? Our final will be 9 meters x hat plus 5 meters y hat. Our final minus our initial. I subtract the components from each other, so I take this 9, subtract that 2 from it. So that would be 7 meters x hat. I take this 5, subtract this 5 from it. So that'd be plus 0 y hat. Just ignore that. And so velocity is going to be our final minus our initial vectors over t, which would be 7 meters over 5 seconds x hat, which is 1.4 meters per second x hat. Follow? Origin of coordinate system didn't matter. And that's important because, you know, if I look at a map where I start drawing my coordinate system, I mean, it shouldn't affect anything about how fast you're going, you know, that's something I construct, not what's actually going on. All right, so let's go ahead and let's do a slightly more complicated example. We'll do it with 2 directions now, X, Y. Let's say that my initial position, Ri, has a magnitude of 20 meters at an angle of 30 degrees. Can you see this? Maybe you not see this. 30 degrees north of the x-axis, or above the x-axis. I'll call this our initial. Let's say our final is over here. It's 100 meters. It has an angle of 45 degrees north of the negative y-axis. If I wanted to draw that displacement vector, what would it look like? Pointing from your initial to your final position. So delta R would look like this. So, and let's say that the time it took to go from our initial to our final is 20 seconds. So what is the velocity and the displacement? Question mark. So this one is a little bit more complicated because you got to break up those first things into those first vectors into components. See if you can go ahead and do that.
So you subtract. Yeah, and your x's. And then that's your the hump. Yeah. You got it.
Who's still working? We'll go ahead and do that then. See if everything's more or less done. Okay. Let's look at our initial. first of all, we want to write that out in x and y components. So that's this thing here. It has a magnitude of 20 meters, points 30 degrees above the x-axis. So what would be the x component of that? 20 meters cosine of 30 degrees x hat. And then it points also in the positive y direction, so plus 20 meters sine of 30 degrees y hat. And this was 17, right?
0.3.
17.3 meters x hat plus 10 meters y hat. Good? All right, let's do our final. So the final position would be, well, it points in the negative x direction, right? So I do minus 100 meters cosine of 45 degrees x hat. We follow that? I got that. So that cosine of 45 degrees would be this length over this length, which is 100 meters. And so if I solve for just the x component, which would be this length, I have this. And there's a minus sign that points in the minus direction. I have to kind of add that by hand, knowing that it points in the negative x direction. How much does it point in the y direction? So it would be 100 meters sine of 45 degrees y hat. What are those numbers?
Negative 70.7.
Yeah, you're right, it's 1 over root 2. But the negative, what's that, what was it, 70?
Yeah, negative 7.7.
7 meters. X hat, and the same thing here.
Positive.
Okay. Now, if I want to do R final minus R initial, what would I do? If I take this x component and subtract this x component from it, so that's going to be negative 70.7 minus 17.3 meters x hat. And then I take this y hat and subtract this from it. Plus 70.7 minus 10 meters y hat. So minus a minus, what is that? Even more minus.
Positive. I mean, minus.
So that's, that would be 88. Minus 88.0 meters x hat plus 60.7 meters y hat. You guys read that? Yeah.
Why does R final not equal 0?
This is the R final, right?
Yeah, but if it's negative 70.7 plus the 70.7.
Yeah. So these are x hat, y hat. You can't ever add an x hat to a y hat. This just tells you it goes 70.7 meters in the negative x direction. This is 70.7 meters in the y direction. Good question. All right. I guarantee somebody on the test is gonna say that something like that would be 0.
So if we were 45 meters, we would only have to solve for either the x step or the y hat, and that would give us, correct?
Yeah. Yeah. Yeah, the cosine of a 45, cosine of a 45 degree is the same thing as sine of 45
This
degrees.
direction.
Okay,
Is it?
Toe to heel, this toe is what it's at. Our F would go to our initial and then our delta would be.
For the 45 degrees, right?
3:30.
all right, I gotta finish it up, I'm almost done. I'll finish up this problem, but yeah.
The way you do your delta bar, tail thing, you get that form when they line up.
That's right. So our initial plus delta R. All right, let's go ahead and do B. It's gonna be delta R divided by the constant of, which would be 20 seconds. And so I just take each of those and divide it by 20 seconds, so that'd be minus 88.0 over 20 meters per second, that's that, plus,
Dr. Dale.
yeah.
Aren't X hat and Y hat flipped for our initial?
I don't think so.
Okay.
It points up that far in the y direction.
Yeah, the Y is
Sine.
off,
Okay.
adjacent over.
Yeah. The y is an opposite over hypotenuse. So,
What? Oh, yeah.
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 Opposite.
Yeah.
Okay, so then we get 60.7 over 20 meters per second. Y hat, and you could then go ahead and evaluate these and see what that is, okay? That'd be your velocity vector. All right, well, we'll have to call it the day today. We'll do acceleration next, we'll do acceleration tomorrow.
Right, because you're thinking of cosine, but it's sine.
I need to get to that.